while implementing micro robots, there is a need to understand the overall environment, so that based on the environment appropriately we can design the micro robot. As I discussed earlier, on a macro scale, so when we are trying to design a robot, so it has several other features. So one of the features, like so we have a macro level actuator, so we have a sensors where these sensors can be incorporated appropriately, and the necessary feedback can be collected, and appropriately the design changes and the considerations can be taken into the integration of these robots, and then we can deploy these robots for different applications. However, with reference to micro robotic perspective point of view, so there are several constraints which will try to participate in designing such kind of robots. So one of the constraint includes, let us take an example of a simple AGV. So when we try to develop this AGV on a macro level, so in the case of AGVs, we have a propulsion system which is nothing but the wheels which are being incorporated over here, and the different controllers which are being stacked over here, and then for appropriate communication we have an antenna in place, and then the most important aspect is the locomotion perspective point of view. So here an external power source can be deployed, or a battery can be deployed, and it can be charged and it can be used for the movement of the system. However, when we try to reduce it to a micro level, there are different challenges which persist. So some of the challenges includes like a kind of a influence of surface tension, influence of inertia, influence of friction, influence of air flow, influence of viscosity, etc. So many aspects which comes into the picture, and one of the key challenges which are involved in fabricating such kind of micro robots are like we may need to scale down from a macro level to a micro level appropriately, and we may need to consider these losses appropriately while we are designing this micro robotic system. So the main motto of this particular module to give a necessary exposure to the participants about the different scaling laws, about the parameters involved in the scaling laws. So we have selected few specific domain, and we will be discussing about the scaling laws which are implemented for this particular domain. So when we try to talk about scaling laws, so these scaling laws describes how the attribute of a system change as its size increases or decreases. So it explains why object, creature and physical phenomenon act differently at various scales. So these differences occurs because a physical force like gravity, surface tension, inertia, friction, etc. do not scale the same way with the size. So it gets changed with reference to the different parameters. Now when we try to consider this scaling, so in the case of a traditional engineering principles, it do not apply at small scales. Basically we may require a new approach, and with reference to force perspective point of view, force behaves differently and the surface forces dominate and the gravity becomes negligible. And as far as motion perspective point of view, so motion requires an alternative strategies, example this helical propulsion, oscillating magnetic field, etc., which participates in this system. Now one of the key challenges which are involved is the powering of this micro robot is considered to be a key challenge. So in this we may require a kind of an external energy source. This external energy source will have a kind of a non-contact based powering, so which will be helpful for powering such kind of micro robots. And as far as manufacturing methods perspective point of view, so we may need to deploy a specific microfabrication techniques which will cater the overall micro robotics related systems. Now when we try to look into the overall scaling laws, so these scaling laws describes how physical property changes as the size of the system change, or on these laws are based on the mathematical relationship between the different physical quantities. Now there are generally two types of scaling laws that are being applicable to the design of microsystem. The first type of scaling laws is strictly depend on the size of the physical object, such as scaling a geometry. Examples of this is a law includes scaling of rigid body dynamics, electrostatic and electromagnetic forces. The second type of scaling law involves scaling of a phenomenological behavior of a microsystems. Now, let us see the basic mathematical form of a scaling law. So, let us consider a function describing a system with some parameters which are dimensionless. So, let us consider this W term and the other parameters that are geometry dependent as V terms. Now, V naught, Vn, W0, Wn is f of V naught to Vn and W naught to Wn equals y. So, if we now assume that we scale all geometrical dimensions by a factor k, we get kV naught, kV, W0, Wn, f V naught, Vn, W0 and Wn, which is nothing but the ksy. The parameter s is the scaling factor. So, by convection we can use Ls to describe the dimensional scaling effect on the property. Okay. Now, let us discuss about the scaling effect in the overall surface and volume ratio. So, as surface can be expressed in terms of a double integral summation over a given domain. So, let us consider this as a domain. So, in this domain, so we are representing this domain as omega and we are representing this domain, we are representing this domain as ohm. And there is a point ds. Okay. So, So, the surface can be represented in terms of double integral summation over a given domain O. If we scale down the integration domain, so we can show the surface scale by that the surface scales by L squared, that is f of x of y is directly proportional to the integral ohm ds, which is equal to the integral dx dy. So, f of x of y, that is kx of ky, f of kx ky is directly proportional to k omega k ohm ds, k ohm dkx dky, which is equal to k squared integral ohm dx dy, which is k squared f of x comma y. So, the same method can be applied on a volume and we can show that the volume scales by L cube. Now, if we try to nomenclate it, length equals L1, surface equals L2 and volume equal L3. So, from this simple analysis, it is clear that the physical properties that are proportional to volume will become much less significant than surface related to ones. Now, let us examine some of the other various physical properties like mass, moment of inertia, spring force and the oscillatory frequency. So, the scaling effect on the mass can be calculated using a definition of the mass as density is an intensive variable. And it is independent of the geometrical dimension. Of the geometrical dimension. Now the mass scales down as volume, or L cube, that is m equals PV K Pk P dash equals K naught P and V K V dash equals K3 V, that is m dash equals K3 m. Similarly, when we try to consider the moment of inertia, so by definition the moment of inertia is the distribution of points of a solid around giving an axis around a given axis. Now with reference to mathematical perspective point of view, so mathematically it can be represented as I del equals m epsilon s hm square dm. So the m is a point which is being represented over here, and then the m is the point which belongs to the surface belonging to the surface S, and h is the point of axis from which the moment of inertia is calculated. Now when we try to look into the overall scaling factor, so we can represent this as I del by ay bx ax f of x comma y dx dy, which is k I del dash kby by kay kbx by kax f of x of y dx dy. So from this we can estimate the scaling factor as I del dash equals by ay bs as f of x dash y dash dx dash dy dash, which is nothing but k power 4 I del. Now similar can be established for the spring force and the oscillating frequency. In the case of spring force, so we consider the spring stiffness. The stiffness of the spring is considered to be constant. and the spring force scale like the length we have or F equals K del L. So, the oscillating frequencies can be represented as S F equals 1 by 2 pi root of K by M, which is directly proportional to 3 by 2. Now, when scaling the spring dimensions down, assuming its stiffness, it is constant and the natural frequency goes up. Dimensions down, assuming its stiffness is constant, the natural frequency goes up. Now, let us take and the influence of scaling effect with reference to the electrical properties as well as the inductance properties. The same methodology can be applied to any property that involves physical dimension. So, to evaluate the electrical resistance, we can mention it as R equals rho L by S K R dash rho K plus 1 L by K plus 2 S equals K power minus 1 rho L by S equals K minus 1 R, where L is the length of the conductor element being considered, S is the surface cross section, and rho is the resistivity. In particular, so when we try to consider the scaling law L minus 1, which basically indicates the resistivity increase with scale reduction, it should be stressed that we are making the assumption that electrical resistance can still be described with the law of formulated. A nanometer scale quantum effect starts to be observable, and therefore, the law above is no longer suitable. Similarly, we can also estimate the scaling loss of the capacitance, which is this is the resistance. In the case of capacitance perspective point of view, epsilon S by D K C dash K plus 2 S by K plus 1 D, which is nothing but K1 epsilon S by D equals K1 C, where S is the surface considered, D is the distance separating the two surface on which the potential is applied, and epsilon is the permittivity of the medium. Now, in a similar fashion, when we try to consider for an inductance, so the magnetic field, ideally when we try to talk about inductance, inductance is heavily used in solenoid. These solenoid, so when we consider a solenoid with N turns, of wire of length L and current I through the coil, is given by B equals mu Ni by L, and the magnetic energy is stored in the solenoid is E equals P square by 2 mu P. So, the magnetic energy in the coil scales as, so assuming the current density remains constant and keeping the number of turns constant, the magnetic energy in a coil scales as L power 5. Now, as far as the scaling laws are concerned, so ideally when we try to map it, so we normally used to follow this square cube law. So, this law states that as an object grows, its volume increase faster than its surface area. So, normally the surface area is considered as L, which is directionally proportional to L square, and volume is directionally proportional to L cube. So, S by V is normally represented as L minus 1. For example, so in the case of an elephant, the S by V is 10 power minus 4, and in the case of a dragonfly, the S by V is considered to be 10 power minus 1 mm. So, when we try to observe the overall effect of geometric scaling in a micro robot, at small scales, a higher surface area to volume ratio is considered, a faster heat dissipation and a stronger adhesion forces are considered. Whereas, a fluid dynamic shift, when we try to consider a fluid dynamic shift, the motion basically dominated by the viscosity, which is nothing but a kind of a low Reynolds number which is considered. Now, when we try to consider an electromagnetic forces, when it becomes a dominant, gravity is negligible at the micro scale. However, at the larger scales, the volume grows faster than the surface area. The structural integrity must be considered. And when we try to consider a mass and an inertia, so the motion realize a momentum and an external force which exhibits over here. Now, let us discuss about the scaling laws in a rigid body dynamics. So, as far as in a rigid body dynamics is concerned, let us consider a rigid body having a mass m traveling from one place to another at a distance s. So, like there are two masses are there, the mass which is moving from one end to another end where s is being considered. So, s is directly proportional to L and the L stands for the linear scale. Similarly, s is ut plus half at squared, since it is the movement of the particle, and when u is equal to 0 and a is 2s of t squared. Also, the dynamic force is considered as ma, where m is the particle mass and a is the acceleration due to gravity, and f is the acceleration, and f is the 2s by mt squared ll cube by t power 2. So, when we try to closely look into this, for a rigid solid traveling, traveling from one position to another position, let us consider the solid travels S. So, S is directly proportional to L, where L stands for the linear scale. The velocity V is V equals S by T, and hence V is directionally proportional to L T power minus 1, in which T is the time required for the travel. So, overall, once we consider S equals V naught T plus half A T square. So, V naught is the initial velocity and alpha is the acceleration. So, V naught equals 0, alpha is 2S by T square. So, the dynamic force F for a Newton's second law can be expressed as F equals ma 2S m by T squared L L3 T power minus 2. So, appropriately it has a kind of a deviation in the tremor force scaling method, which we will be discussing in the upcoming classes.